Hi, I'm Marty Dwyer with boatanchoraudio. We have something here you audiophiles and experimenters might be interested in. It's nothing more than your twin T notch filter. However, instead of building it on a printed circuit board by itself, we put this on a printed circuit board that has a number of terminal blocks that can be used to change your frequency determining components without any soldering. In other words, this is a development board. Now, why a development board instead of a breadboard? Well, there's two main reasons. First of all, breadboards have their use. They're easy to use. It's easy to swap components in and out. But two reasons not to use them is they do have straight capacitance, and there's always the danger of loose connections, loose components. Anyway, what we have here is a breadboard, or rather a printed circuit board, that has a number of terminal blocks on it. So you can connect or disconnect, reconnect various frequency determining components such as your resistors and your capacitors. Now before I show you the board, let's take a quick look at the schematic. Now as you can see, it's nothing more than your traditional twin T notch filter. There are a few changes here. They're nothing basic. They're minor changes. If you look on the schematic here, you'll see a number of items marked TB2, TB7, TP this, TP that. These are merely terminal blocks, two terminal blocks or two position terminal blocks where you can put in additional resistors and capacitors. These, of course, are the components that determine how this notch filter works, what frequencies to cue, how deep the notch, so on and so forth. Looking at it very quickly, you'll see nothing more than a buffer for the input, a buffer for the output. If you look carefully, you'll see IC 1.2, IC 1.3. Now that is designed to adjust the feedback going into the notch filter. We do that in order to adjust the cue. In other words, adjust the width of the notch. We'll show you some shots we've taken from our network analyzer and give you a better idea of what we're talking about. Anyway, here's the finished product. As you can see, it's your standard printed circuit board. There's a number of components on it. The green components are your terminal blocks. Again, they can be used to swap out components, resistors, capacitors. That'll change completely how this works. It'll change the notch frequency, the depth, and the cue. Looking at it, you also see two blue blocks on there. They're just trimmer resistors, trimmer pots. We have the on and off switch, and of course a jack for your voltage. The voltage on this, by the way, is anything from about 15 to 24 volts. It's very low current draw, maybe 10 to 12 mils. So if you put a couple of 9-volt batteries in series, you have a battery-powered notch filter. You can move it around wherever you need to go. Also, before we get into the network analyzer, let me show you the bare printed circuit board, and it gives you a better idea how things are laid out. If you take a look at it, you'll see what we've seen on the previous board, minus the components, of course. But it gives you a better idea how it's laid out. At the top, we have a couple of terminal blocks, RF1, RF2, that just enables you to swap out a couple of resistors. We have an RF1V, that's just a trimmer resistor. Going down the T, we have CF1 where you can put in a capacitors. At the very bottom, we have CF2, CF3. That allows you to change capacitors very easily, no soldering necessary. We have RF3V, excuse me, that's just another trimmer capacitor, or trimmer resistor, and the usual filters. Schematic again, you'll see at the very bottom, this is powered through a rail splitter. Now I'll go through this very briefly. I've had better luck using rail splitters using a split power supply where you have VCC positive, VCC negative, rather than having a single-ended power supply. So we have a power supply in here that gives you your VCC plus and VCC negative. That's just my own preference. I've had better luck with it that way. All right, let's take a look at the results from the network analyzer. Now, the first result here shows us centered about 1.02 kilocycles, something like that, a little over 1 kc. As you can see, it's a pretty deep notch. It looks good. It's about minus 73 dB. Now, offhand, looking at it, it looks pretty good. But if you look again, say at 2 kc, where the second harmonic is, some of that second harmonic is going to leak in there because the Q is so low. Now, here's where we make the deal with the devil. Here's another shot, same circuit, same network analyzer, only this time we narrowed the Q. Now, by doing that, we also reduced the depth of the notch. It's down to about minus 50 dB or so. But it's a lot sharper now, and any signal that would be coming in through the second harmonic at 2 kc is greatly attenuated. So something like this, adjusted like this, would be suitable for a distortion meter. Again, the notch is fully adjustable. You connect a pot right on terminals TB8 and TB9. That adjusts the feedback that's going in to the filter, and thereby adjusting the pot. By the way, the network analyzer we use is a analog discovery. We use the network analyzer function on that. We're very pleased with that. Anyway, we hope you liked this video. If you have any comments, leave them below. We'll get back to you as soon as we can. In the meantime, keep those electrons flowing. Talk to you later.